All right, we've been talking here in class about an exam here, and I think what we're looking at right now is a week from Monday, okay? Which, and I don't have a calendar in front of me, but I can do math, so what do we got? We got 13, 14, 15, oh, is that the 22nd? No, it is 6, it's the 23rd, right? 23rd, okay. So I think that's what we're gonna do unless there's some compelling reason to do otherwise. So I think we'll look at that. So Monday the 23rd, we're looking at an exam, I think. And I'll get you a review sheet for that probably next week. It's already online if you just want to get it there. What I have for review is I just list out the topics, and also I've got some old test questions so you get some idea what my tests look like. I don't know, maybe on average 4 questions to 8, somewhere in there. So they're not like those little short answer deals. They're a little bit longer. They're like homework problems, basically. I mean, it's nothing. Just doing homework-like problems. Okay. But if you're curious right now, have a look in Moodle. Okay, there's some review stuff in there. Now, let's see. So that'll be in here. That'll be from 1 o'clock to basically, simply put 2 o'clock. But then also there's online students. So usually what I do for online students is have one in the evening, usually 6 o'clock to 7 o'clock. So that would be Monday also. Now, if you need any accommodations on this stuff, let me know and we'll get that all lined out. If you're an online student and you're not here, if you're somewhere else, you need to find a testing center, and I need to get an email from a testing center. It has to be in America, and it has to be a testing center at a school, that regularly proctors tests. So that's that's kind of the rules on that, okay? And so we'll just kind of start with that, and then I'll kind of fill you in next week. I'll get you a review. We'll go over it and all that. There's going to be a lot of 3D on this thing, and I would really suggest that you just learn the steps. Do this, do that, do this. To get a force vector, blah, bang, bang, bang. To get a projection on a line, do this, do. Just figure it out that way, and then just do it on the test, okay? And the other thing I'll just mention on this one, I'm thinking about it, is typically on these tests, this stuff is very time consuming. So sometimes what I'll do is I'll have you find vectors on page 1 and then use those vectors to accomplish different things on the rest of the problems. So you just find vectors once rather than having you do it over and over again. Okay, so that's something, I might do something like that. I don't know, I haven't made it up yet, so I don't really know, but that's something I've done in the past, okay? And I have a spreadsheet, so if you bust the vector on page 1, if you make a mistake, I can follow that through on the next problems to make sure that, with your incorrect vector, you're doing the proper things. That would be fine, if you know what I mean on that, okay? So, but just be aware of that. Sometimes I've done that, I've had people find the vectors every time on every problem, which, is kind of what I'm trying to avoid having to do. So just realize I might do something like that and be aware of it, okay? All right. Any general questions on that or anything like that?
What's the rule on calculators?
The rule on calculators is they have to be non-programmable. Okay? So, they got to be just straight up. The common ones are the TI, I think they're 36s. Yeah, okay. But the reason for that is a few reasons. One is a lot of OSU classes require that now. The FE exam requires that. They only have certain approved calculators. And the thing is, you can get chips now, not so much for statics, but some of the classes I teach down the line, you can just get programs that just drop them in your calculator, and then you can just input and bang, you get answers right out. So, that's the reason for that, to avoid that scenario there. Especially in strength materials, there's lots of programs out there available to work through that stuff. So it's kind of a blanket policy, okay? They have a similar one in physics, I'm thinking. And, so it's the same sort of thing as them. The one I often see is a TI 36. Now, I'll bring a few extra calculators with me, but don't count on me. Now, the one thing I've seen on that, I'll give you all the little warnings here, but if you normally use, a more high-powered calculator, get what you're going to use and use it before you come to the test, because the syntax is a little different on every calculator. And I've seen people with a calculator that they've never used before on a test, and that's a real bad idea, because you're kind of hunting around trying to figure out how to take a square root or how to do this or that, and you don't have time to be screwing around with that. So, get the calculator figured out before you take the test on it, okay? Right. So, other questions on that? Okay. All right. We got some homework coming due tomorrow. So why don't we have a look? Something that looks like this. Is it turned the other way on yours? It's kind of oriented vertically, right? The box.
Yeah.
Okay. So
All the old stuff is correct.
yeah, except for the dimensions, right? Everything else. Okay.
Yeah.
Yeah, great. Okay. So this is kind of a basic moment problem here. It just kind of covers the couple of ideas on there. One is that you use trigonometry to break down the force vector into x and y components, and also then that you find the moments combining unlike force and distances. So you'll use fx and dy and fy and dx. Okay. And then you add up the results. So to find a net moment is just an additive process. You just add stuff up to get the proper answer there. So, I don't know, are there any questions on this thing? I mean, actually, yours should be oriented this way. I changed this and just never got around to it here in my little key. So 0.24 meters, 0.72 meters, and then we've got the force, same force, so 820 newtons at 55 degrees. So this is an awful lot like what we did in class. We got any questions on that?
What page is that on?
Oh,
7.
yeah, 7. Yeah, it's page 7. Okay. So you just go summa MA, and you'll break this thing down into components, and then you'll get that component, and then you'll get this other, and you'll have to add them up, and actually you're going to subtract one and add one and put them together and get the total answer. Should be negative 177 newton meters, I think. So when you work down through there, you should get summa moments about A is negative 107 newton meters. That's one way to write it. You could also write it this way if you like. Okay, we good on that one? Any questions?
On the test, how do you prefer us writing it? Is it one or the other?
Yeah, it's one or the other. I don't quite, I know there's always questions like that. I kind of like the way in the bottom, because it leaves no room for error at all. It just says it's this big and it goes this way, and it's completely unambiguous. But I'm not a real stickler on that stuff, what I mean. Just show me clearly what you're doing and what the answer is. Should be okay. All right, the next one is a little bit more advanced, you might say. So now we got two forces, okay? So what you want to do here is you want to break these things down into vectors. So you want to take those forces and break them down into vectors is what you want to do. So what you would do with that top force, for instance, is you would take 50 and use cosine and sine and break it into the two x and y components. So cosine 50 times 1900 and that's, I think it's 1221. And then sine 50 of 1900. And that's 1455. All right, so then what you're doing is you can take the two components and put them on there and replace the original force. You know, I just go ahead and draw them on there if I need to. That way it's nice and clear what I'm up to. That one's gone now. And you can do the same thing with this other one here at B, okay? Like so. And then what you do for a moment, you know, you're going to go sum of moments about A, and you're going to go sum of F. Well, what you're going to do here when you combine things for moments is you take X components of moment with Y distances, and you take Y components, excuse me, X components of force with Y distances, and Y components of force with X distances. Now those aren't dy dx like calculus, those are just distances. Okay, and that's how you generate moments. So remember that, you don't combine like components to get moments, you combine unlike components to get moments. That's kind of what a wrenching action is. When you push on a wrench, you're pushing perpendicular to the line of the wrench, right? So they're going in, the force and the distance are in different directions. So what you can do with that then is take, you know, you're going to get the total moment about A. And what do we got there? We've got 1455 newtons. That's a Y component. There's an X distance, 1.6 meters. That's going to come around this way. That's clockwise, so that'll get a minus. And then you'll have the other one, and then et cetera, et cetera. You just kind of add all that stuff together. And what you ought to get is positive 154 Newton meters when you're done. Positive means the net moment is counterclockwise. Yeah, question there?
So is that saying that it takes 1455 newtons to go down basically to B, and then it'll go that way? So as far as rotation, I understand the idea behind the 1455 newtons and the 1221 newtons. I understand that those are the vector directions.
Yeah.
But is that what it takes to get from the very top to point B and then B to rotate? Like,
well, you can kind of, let's see. Well, what you can do, you can take a force and apply it anywhere you want along its line of action. I mean, that's the rule on that. So that 1455 acts anywhere on this yellow line. So I guess you could say, you know, you could put it down there and then combine it with this distance. You know, that's really what's going on there. Does that answer your question? Okay, so yeah, you can extend those forces and put them anywhere you like. Also on their line of action, I would call it. Okay. All right. And your intent there is to get distances that are perpendicular to the force. That's why I'm putting that one force down at B. Okay. Questions on that? Other questions? All right. Oh, weird. No, I have that. 2. All right, now this one is maybe a little trickier. It might be helpful to kind of do a little trick on this one. Now, if you do this straight up the way that I was showing you, I would probably end up doing something like this. I would take I'd figure out that angle there, which looks like 29 degrees to me, okay? So that's 29. And then I would find this distance by taking cosine 29 times 0.4 to the weight, okay? So I'd do that. And then I would also find these two distances like that, and I didn't draw that quite right, but I would find these right angle distances, x and y, to get from A out here to the end of this rod. And then I would take the cable force and break that up into components also, something like that. Okay. Now that's a bit of work. I mean, it's not that bad, but it is a little bit of work. And I think there's a little bit quicker way to do this, so why don't we look at the quicker way to do it. What you'd have to do here on this also, in addition to what I'm showing, is also do parallel angles there, and that's 29 degrees, right? So that would leave 20 up here, wouldn't it? So there would be a little bit of messing around on that to kind of, get everything lined out and figure out, what that net moment is. There's a quicker way to do it. Okay, so why don't we look at the trick on this one? Yeah, you want to spin your axes on this a little bit. So what you want to do on this is to orient your axes along that rod is what you want to do. So I think it would be a lot easier if you approach this problem like this. X and Y. And you can always orient your axes as you wish, okay? There's no rule that says they have to be horizontal and vertical. All right, now, and you'll notice that those angles that you're given lend themselves to doing this. Now, it works better, it works well with the angles that you're given, the given information. So if you do this, you've got the distances along the x-axis. And then you've got the angles that the forces make with that x-axis. And why don't we call it x prime, because it's not the usual x-axis. So x prime and y prime. So you got the distances right along the x prime axis, and you've got the angles from the forces to the x prime axis. So you can do a bit of trig and get that thing worked out along the axes. So that's how I would approach this one. It's just quicker and easier. Okay, so that's going to be the x prime axis, like so. And then you'll have a y prime axis like that. And that's point A. And then you've got the weight, of course, it goes directly down. And then you've got the cable force like that. Now what you got in here is 61 degrees and then 49 degrees, right? And then you've got 0.4 meters and 0.4 meters. All right, so that's what you're dealing with there. So what you could do now is you can take those forces and break them up. Okay. So I would break this force up into an x prime component and a y prime component like that. Or excuse me, I've reversed that. So, well, the x prime and y prime. And then I would take the other force, the weight, and break that into a y prime and an x prime force like that, okay? You all okay with that? And see, now what you've got the angles to do that very quickly. You don't have to do any of the figuring out the angles like I did just a couple minutes ago for the standard XY axes. And you've got the distances measured along the x prime axis, so you're pretty much good to go. It's pretty straightforward to do this. The other thing that's happening here is that will not cause a moment, right? That has a 0 moment arm, as does the other. So not only the other things I mentioned, but this stuff, a lot of that stuff just cancels out because it goes right through A. And if you push on a bolt, you don't spin it, you just push on it. You need the offset to create a torque, a spin, a moment, whatever you want to call it, okay? So those two cancel out, so you only got to deal with two components. Okay? And then you know the magnitudes of these things, so you could go, 700 newtons, sine of 49, right? That would be the component you'd want. And then that would be, what's the moment arm on that from A?
you don't.
It's 0.4 plus 0.4, so. And is that everybody's looking at that, is that a plus or a minus on that one? Yeah, okay. Now, if you ever got doubts on signs, just check it out, you know? I mean, just like that and push on it. Yeah, sure enough, it's going, whoop. Guess I'm going the wrong way. Here we go. I'll do it from my perspective. Here we go. So that one, it's going counterclockwise. So, you know, you can always, if you ever got doubts on signs on moments, just get a pencil or a little block, an eraser or a credit card or something, push on it, see what the heck it does, you know, tell that way. Okay. So that's positive, and then the other one will be negative, won't it? So you got one other, and then you do the deal on that, add everything up, and you get 276. Okay, so that's how I would approach this, and this is a nice little trick to know about. Every now and again, this can be a handy way to do something. Could save you a bunch of messing around. So we doing all right with that? Got any questions?
Do you want your answers in positive and negative, or in counterclockwise or clockwise? Yeah.
It's not a huge deal. I'm used to positive, negative. CW and CCW, I might have to kind of look at for a minute. So just plus or minus probably work better. Or like I say, you can just put an arrow on them too if you like. That's fine. Okay, now you good with those x prime components being 0 for moment? Okay. All right. As they push right through A. And then the other thing on that is there's no direct connection between the sign on the force and the sign on the moment. Sign on the force is up, down, left, right. Sign on the moment, I don't worry about the sign on the force. I just look and ask myself, does this thing cause the object to spin clockwise negative or counterclockwise positive? So don't try and put the sign on the force that you put into the equation. That messes things up. And then the other thing I've seen people do is they talk about X moments and Y moments. And in 2D, there is no such thing as these. So don't be putting that on your paper. That's not really a relevant way to subscript those. Okay. Moments is to twist, however it gets started. It doesn't matter if it came from an X force or a Y force or whatever. It doesn't make any difference. Okay.
So it's always the moment at the point?
Yeah, it's a moment. I would say about a point is usually the term I use, but whatever, yeah. It's a moment. Okay. We okay with that? We got any questions on that stuff? All right. Okay, we're good. Okay, why don't we look some more at 3D moments here? This is the last topic that'll be on the test, this moment stuff. We'll probably have it finished by tomorrow. So this 3D stuff, it gets a little trickier than the 2D. 2D, I just use trig and combine stuff and look at it and figure it out in that fashion. 3D is a little bit more formal, or I don't know quite what the right word is. But so the first thing is you name moments after the axis they spin about, okay? So an X moment is a moment that twists about a line parallel to the X axis. That's what an X moment is. So all 2D moments are Z moments because they all twist about a line parallel to the Z axis. So what I think of the moment as being a wheel and the moment vector as the axle of the wheel. Okay? So if a moment is spinning in the XY plane, which any 2D moment is, that's the wheel. Think of that little arrow you draw as being the part of a wheel. The axle of the wheel is normal to that wheel, right? always. I mean, that's how axles work. So the moment vector is the axle. That's how I remember that, okay? So when you're doing 3D moments, you got twists about a line parallel to the x-axis, twists about lines parallel to the y-axis, and twists about lines parallel to the z, and those are your three components of moment. X, Y, Z, which are designated by the unit vector components I, J, K. Right? So that's how those are called out. All right, now the theory behind this is you look at how these things spin. We were working on this problem here, we did it visually. So we took that vector from B to C and we put it at C. We broke it up, the force vector, into its three components, and then we started looking at it and we started kind of trying to figure out how that force would push point C about A. We looked at each component individually and we combined those three components of force with moment arms to get the net moment about A. And we did different visualization approaches to accomplish that. We did like a rod from A to C and looked at how the push at C would rotate the rod about A. We also looked at edges there of that box as being like hinge lines and looked at how those components of force would push a door along those hinges. So the hinge lines are along the axle, they're along the line that points in the proper direction for the moment vector for that component of force. Okay. We also realized that when you create a moment, you combine the three components together. The subscripts on the force, the distance, and the moment itself always take up the three axes, X, Y, and Z. So that example there on the top, we've got a Z force, we've got a Y distance, and the moment is an X. So that's not a coincidence. The three of them will always combine to get you one X, one Y, and one Z. So keep that in mind. That might help you to combine the right force with the right distance. They have different signs. Okay. And then we looked at this and we kind of figured it out. And as is always the case, you know, everyone kind of squints when they look at this and try and visualize, and some people get a little cross-eyed and all that. You know, this can be a little challenging sometimes to figure out, you know. And typically I've found that some people have this innate ability to see stuff in their minds. Some people have less of that ability. That just seems to be how it is. Okay. Now, you can put the force anywhere you want along its line of action, okay? And when we put it at C, we got those two moment vectors in yellow and green. Notice there is not a twist about the x-axis. There's a J and a K twist there. And so that moment vector is 0I plus 57.6J plus 202K. Okay. And the units are Newton meters, which are the units for moments. Okay. We're doing all right with that? Any questions? Okay.
Did you move that point in a different spot? I'm trying to remember what you did. You said you could move that point anywhere on the line of action.
The BC force? Yeah, I put it at C because it was easiest.
Okay.
But I could do it at, what's that?
Why is the X component 0? Wouldn't the upwards part of the force vector cause a moment?
So the 144?
Yeah, wouldn't that cause a moment around the?
When I put it at C, it doesn't because it's right on the x-axis. It's right above the x-axis. So when I put the force at C, the 144 just pushes straight up. All that does is spin that way and cause a twist about the y-axis. Okay. So they're all a little different. Now, if you put it at B, it's a different situation, you know. But when you put it at C, there's no X component directly in that thing. That nothing generates an X component of moment. Yeah, of course.
So is this box hinged on point A alone or AX?
I think the hinges are at the point about which you take moments, because that's what you're looking at, the rotation. Now, the other thing I'll mention to your question is this box really isn't hinged at all. I mean, I'm looking at what the moments are.
Oh.
I use the hinges as a visualization approach so I can kind of see it, but
Okay,
they don't have to
and
be
the
hinges.
hinge you visualize is the one from 8.8.
Well, the hinge just depends on what I'm trying to analyze. It's just a visualization approach.
Okay.
See, what I'm looking at now, what you might say, are the moment that builds up in A. If I'm designing that support in A, this is the moment it has to resist, is really, if I don't want it to break. I mean, that's how I could look at this, maybe. Okay? So the hinges, I just throw in there, you know, just to help me see something. That particular one there, the two green hinges on that line to the right of A, were showing that that moment caused by the 144 was a Y moment, because it would rotate a door open about the Y axis. Okay. Now I could put a moment vector in there. Are there other questions on this? Now I just want to mention too that there's an easier way to do this. You use a mathematical operation called a cross product, and it'll just knock this out for you. But I do want you to kind of understand what a 3D moment is, you know, not just crunch the numbers. That's always something I've got in my mind when I'm teaching this stuff. Sure, anybody can run the formulas, but, you know, so what? I mean, you know, you got to know what the heck you're doing. Anybody can design a mechanical part, but some people do it in ways that machinists can't build. And then machinists get a little angry at the person who designed it in the first place. So we want to try and get around that, you know, see it, be able to see what the heck you're doing. That's why I cover this, okay? All right. Okay, now the moment vector then is 0, I. So I've got this moment vector there, and it's in orange there. So the moment vector is 0, I. So there's no moment about the x-axis. A little bit of moment, 57.6 in the j, which is the y direction, and then 202k. So if I were to plot that up, I'd start at A, because that's where the moment is, and then I would run this vector over 0 in the I, 57.6 in the j, and quite a bit more than that, 202 in the k. So there's the moment vector. I've got it in blue now. Now the moment itself twists about that axis. So if there were like a ball joint at A, and that block could rotate any which way, a ball joint is like a ball with a cup around it, and the cup holds the ball and allows the ball to rotate any direction. Ball joints, kind of like U-joints in cars, CV joints, I guess. I don't know, ball joints. You see ball joints different places. Trying to think of a handy one. I don't know, is there a handy quick ball joint that everybody would know other than CV? What's that? Oh, a trailer hitch. Yeah, there we go. Thanks. Trailer hitch should work good. Okay. All right, so if that thing had like a ball joint at A that would allow that block to rotate any which way, and you applied the force from B to C, the block would rotate in a plane normal to that moment vector at A. That's what the block would do if it were allowed to rotate any which way, okay? So the vector is normal to the plane in which the moment occurs. The moment is a wheel, the vector is the axle of the wheel. Okay with that? All right, now let's do this the hard way. Let's put the moment vector at B this time. Now this one's going to get a little bit messier. My goodness. Okay, let's have a look. All right, now I'm not going to spend forever on this, but let's just look at what this stuff's going to do. Okay, how about that 506? What's that going to do? It's going to cut under A, isn't it? And then what's it going to do? It's going to push like so. It's going to cut under A, and then it'll wrap around A like that. You all with me there? So, okay, if this were, let's see. So think of that as just extending that thing out there. It'll go under A, and then it'll wrap around A, okay? So what type of moment is that?
Negative.
It's, yeah, it is negative. What's the sign on the thing? Or, yeah, what, not sign, that's not the sign, the subscript, I mean, I'm sorry. What's that? J? No, it's not. Remember, it twists about, what axis does it twist around? X, yeah, so that's an I. What's the moment arm for that? That's the forced error. The moment arm is which? The distance. Yeah, 0.2 meters, okay? So what I'm doing there, I've got an Fy, right? It's actually a negative Fy, but so what? And then I've got a Z, a Z distance, D sub Z. I'm not going to bother with signs here, okay? I don't want to do that. And then what I get out of that is an MX, okay? So that's an I component. So again, you always use the three letters when you put the three things together. And someone was saying that's a negative, and that's right, okay? We okay with that? Now, I'm sure some of you are saying, hey, wait a minute, we didn't have any X component, you know, in the previous one. What's going on here? Well, here's what's going on here. What does the 144 do if I extend that thing up? What does that do about A? Comes around this way, doesn't it? Now, what type of moment is that? It's positive, yeah, and it's an X moment, isn't it? Because that causes a twist about the X-axis. So this time I'm going to have 144 newtons. Moment arm is, yeah, 0.7. Okay, and that's going to be an I also. And I'm pretty sure if you run the numbers there, 0.2 times 506 is going to be just about equal to 0.7 times 144. See, those are going to cancel and zero out is what they're going to do. Okay. All right. Now, how about the 289? What's that going to do? And I'll give you a spoiler alert. There's actually two answers to what that's going to do, depending on how you look at it. So what two things are 289 going to do? Yeah, they're going to go, it's going to go around the Z-axis, and this is going to start getting a little challenging for my little writing skills here, but something like that. It's not the best, but I'll try one more time, but I'll probably make it worse. You know how that goes. Not very happy with that, but that's in the XY plane. And I need to go around the dang origin. It's too far away for one thing. That's right, I'll just take it boldly where no other vector has gone before, then I'll bring it around like that. That's it. Okay, there we go. It's more like Pluto out there. That's a long ways away. So what do we got? We got 289. That's the force. What's the distance on that one? 0.7. And that's a Z, so that's a K, right? And then what else does that thing do? Oh, thanks. Yeah, that goes, so that's a positive, right? So let's get that labeled with its proper sign. If I can get over this stupid thing here. Oh, come on, give me that. Okay, that's positive. And then what else does this thing do? Now this force does something else though, doesn't it? It goes another direction. What?
Well, it goes the other way around. Or it goes the other way around the Z-axis, but not around point A.
Right. So we're looking at just point A. Yeah, it does. And what does it do there? And and there's just different visualizations you can do on this, and I don't know, you know, quite what the magic answer is on this one, but it kind of goes like that, doesn't it? And think of hinging this axis here that goes through A like that. It spins that door, and what's the sign on that one? Yeah, positive. So that's 289 newtons. And what's the moment arm on that one? Yeah, 0.2 meters. That's a K also, okay? No, it's not a K, I'm sorry. I'm screwing up. Yeah, that's a J, my bad. J. There we go, J. Oops. All right, now this stuff, like I say, some people could just go, yeah, I see it. Some people got to work at it some more. You know, it's different. I can always tell looking around. You know, some people just see it, some don't. It's just there's some, I don't know. It's okay if you don't, because we got a little slicker way just to knock these things out without having to look at them and squint so much and twirl our fingers around. You know, there's other ways to do this, but that's what's happening there. Okay. So when you combine those three things together, you get something like that. And see, that resolves to the same answer that we had before, same moment vector. So it really doesn't matter where you put the moment, it'll work out, okay? So where you put the force, I mean. Now, if I were doing this, I would put the force at C because it's the simplest way to calculate the answer. But you could put it at B or any other point in that line of action. It'll come out. Things will cancel and it'll just work out. The moment is what it is. And wherever you put it on that line of action, it'll work out, okay? All right. So you could do it, you know, wherever you want to put it, okay? Yes?
I don't get why that works out, because if you were to put it, like it's supposed to be on the line of action, like along A.
The line of action doesn't go through A. I mean, it goes past A over here.
I'm just saying, if you were to put that up a little bit, like this motion wouldn't even move it.
Yeah, but there would be you'd move it in and out. No, you can't, you move it all directions at once when you follow that line. So if you don't get a certain action from what you got here, you'll get some sort of compensating action from a different dimension. And the best example is this generated no X moment whatsoever. When we moved it back here, we got two X moments that canceled out. So things kind of compensate if you move along that angle. One effect cancels another. Not the best I got. Okay. Okay. Okay, so that's how you, that's the root of this. That's really what you look at, okay? Now, this is kind of hard to do though, and it's not reliable. It's easy to make mistakes. So once again, the mathematicians come to our rescue here. They came up with this thing called a cross product. And if you're in 254, maybe you've had this already, okay? If you're not, some of you don't even take 254, so I give you the cross product and put it right on your formula sheet. So the easiest way to do moments, and the way I'd suggest doing them, is using this mathematical operation called a cross product. And again, I don't know why mathematicians came up with this. I don't know, maybe it was to do 3D moments, I don't know, but somebody just came up with this thing. So a cross product, you cross two vectors, A and B, and you get a third vector now, C. Okay? So a dot product, you get a magnitude, but a cross product, you get a vector. The magnitude of vector C is the magnitude of A times the magnitude of B times the sine of the angle in between. Okay? C is normal to the plane formed by A and B, and you use the right-hand rule to determine its direction. Okay? So you take your fingers, point them in the direction of A, curl them towards B, your thumb points in the direction of C. So C has a magnitude of AB sine theta, and then a direction that is normal to the plane of A and B determined by the right-hand rule. So if you're looking how to compute this thing, you just use this basic AB sine theta thing for the magnitude. Now, if you cross like vectors together, the angle between them is 0, and the sine of 0 is 0. So when you cross like vectors together, you get 0. When you cross unlike unit vectors together, what you have is A and B are the magnitudes of the two unit vectors. That comes out to be 1. The sine of the angle between is 90, and the sine of 90 is 1. So any time you do a cross of unit vectors, you're either going to get 0 if they're like, or 1 if they're unlike. Okay. And then you just use the right-hand rule to determine the direction of that vector of magnitude 1 that you generate when you cross unlike unit vectors. Okay? So the like vectors go to 0. When you cross them, the unlike unit vectors go to another unit vector. So if you've got, let's just say we've got x, y, and z unit vectors, what, I, j, and k. So if you take I, so point your fingers in the x direction, curl them towards the y, your thumb points in the positive z. So I cross with k is I cross with j is a positive k. Point your fingers in the direction of I, which is in the x-axis. Curl them up towards z. Your thumb points into the page or into the board. So I cross with k gets you a negative j, et cetera, et cetera. So when you cross unlike unit vectors together, you get the results shown. Okay, so you always have all 3 unit vectors represented in that equation, and some of them are positive, half of them are positive, and half are negative. So here's ijk, here's ijk, et cetera, okay? Now, if you take vector A and cross it with vector B, you take every term in A and cross it with every term in B. So you're going to end up with ax bx, I dot I is 0, ax by, I dot j is k, ax bz, I dot k is a negative j, et cetera. Combine the terms together, and that's how you do a cross product. That formula is on your formula sheet. I learned to do it by doing determinants. You might have learned to do it some other way. Well, however you do it is fine. You've got the formula for it on your formula sheet. It's a thing we'll use to do moments with. All right? So we'll call it good here. We'll finish this stuff up tomorrow, I think.